Okay, so what have we been talking about? Essentially, we're talking about systems of equations, right? We have a bunch of inputs, we get a bunch of outputs. And now what we're really interested in as applied mathematicians is, do we have any hope of being able to solve this system? And if we've used this to model something important, does it have a solution? And secondly, how many solutions does it have? You know, if this system is supposed to tell me what the temperature is everywhere, I don't want it giving me 2 or 3 different answers. I want one clear answer. So this is really the topic of the inverse function theorem. So today we're going to mostly go on a journey of trying to build some intuition here into what do we think we can hope to prove. So we'll mostly be looking at some simple examples today and just try to get a handle on what looks like it's true, what looks like it's maybe not true. All right, and then continuing on next class, then we'll start to get very rigorous with all of this. But it's no good proving a theorem if you can't guess what the theorem is and what the hypotheses should be. So what are we doing? We're looking at transformations. So we have transformations now that are square. What I mean by that is that the number of inputs and outputs is the same. Given what we know about systems of linear equations, this is very reasonable if we're going to be able to solve the system. At the very least, the number of inputs and outputs should be the same. Now, we're going to also try to do nonlinear things, so we may need more assumptions, or there may be less that we can prove. All right, and what are we going to say? We're going to say that, let's build up some terminology. F maps x to y. Okay. If y is equal to f of x. And we'd say that y is the image of x. So it's the image of x under this transformation f. So we can talk about the image of a point, but we can also talk about the image of a whole collection of points, a whole set. So if we happen to have a set S that is contained in the domain, okay, then the image of S under F is just going to be the set of all values that this function can reach. So we're going to write F of S is going to be the set of all y such that f of x is equal to y for some x. Yes?
Is it for some or for all?
For some. So we're going to look at, so this will run through all the values of x. Okay. The definition of the set is what values of y we can reach. And for each y, there may be one, or there may be more than one x that can reach it. So for some is correct here, but indeed, this will run us through all the values that we can reach with all the values of x. Right, so we'll start with, and I'll probably draw pictures like this a lot over the next couple classes. And our S goes to something. Okay, why is this important? Well, again, let's say our goal, we want to solve something like this. This is all we do in applied math, is solve f of x equals 0, where f is something. So one question that we should care about is 0 in the image of f? Is there actually any x that can reach 0? Because if there's not, then we've got a problem. Okay, so this is the first question we should worry about. Is 0, this being the 0 vector, is 0 actually in the image of f? Can we reach this at all? Okay, so let's, there is an eraser. Let's take a little example. Okay, so let's say that uv is equal to some function of two variables, which is x squared plus y squared and x squared minus y squared. This is probably going to be one of our favorite examples today. I think we're going to be able to learn a few things from this simple example. Okay, so our first question is, what is the image, say, of all possible inputs? So we have two inputs in here, so all possible inputs is R2. And we want to know what values can we actually reach here. Okay, well, we need to be able to find, for any UV, we need to be able to find some xy that reaches it. So one thing that we could notice is, we're kind of in luck here that this is a simple 2x2 system and things are only quadratic. So we could have maybe a chance of doing things explicitly. That's why this is a good example. We can do a lot of things explicitly here that in the real world we can't. But here we'll do things explicitly and see what properties we get. So what could I do? Well, I could add these together. U plus v equals 2x squared. And I could subtract them. Okay, so what was my question? My question is, which values of uv can I reach? Given uv, can I solve for x and y? Well, in this case, I can say that x squared is u plus v over 2, and y squared is u minus v over 2. So here you start to see there are some conditions that need to be true if we're going to be able to solve this. Right? This has to be a positive, or a non-negative number. This has to be a non-negative number. So to be able to deal with this, we're going to say that, well, the image of R2 is going to be the set of all points in R2 such that u plus v is greater than or equal to 0 and u minus v is greater than or equal to 0. And as long as both of those are true, we can always find a value of x and y that will reach this uv for us. Okay, so if we start here, this is all of R2. Then we say, where does f go? Okay, so here we're somehow on the border, or on one side of the line u equals v. Here we're somehow on one side of the line u equals minus v. So here's the line u equals v, the line u equals minus v. Okay, and what are we requiring? We're requiring that u is bigger than or equal to minus v. So here's u equals minus v. We need to be on this side of it, u is bigger. And then we also need u to be bigger than v. Here's the line u equals v. We need to be on this side of it. Okay, on this side of it, u is bigger. So we're going to get everything in this area as our image. Okay, so even though we start with all of R2, we're certainly not guaranteed to recover all of R2. Right, so if I say, all right, solve, my system that I want to solve is f of xy equals minus 2, 0, then this is not a good model for whatever we're trying to do. It's not going to have a solution. Then the other thing we said we care about is, say there is a solution, how many are there, right? This is one of the big issues of what we call well-posedness of a problem, is we want a solution to exist. The second point is we want the solution to be unique. There should be only one of them. And this starts to come now to the issue of invertibility. So we're going to say that a transformation is invertible you'll also have heard the language one-to-one. Okay? If two different inputs will always give you two different outputs. So if x1 not equal to x2 implies f of x1 is not equal to f of x2. Right, and in 1D, you've seen this as your horizontal line test, right? So something like this would not be invertible because there are, two different values of x that will give me exactly the same value of f. So this would be not invertible. Okay, so another way of thinking about this is, so say here is my domain of f. I guess I call this capital F. Here is my range of f. So these are all the values that we can reach. That's the range or the image. Now, I take any point I like in here. And I want to be able to say that there's one and only one value of x that gave me this point. So I want to be able to go back to here and say there's exactly one place that this could have come from. The fact that this is the range means there is a place that it came from. The fact that it's invertible means there's only one. And that means I could define a new function here. So my function capital F goes this way. It goes from here to here. But now if I have an invertible mapping, I could go the other way around. I could go have a function that takes me from here to here. If it's not invertible, I can't define a function because this point will want to go to multiple different locations, and that's not a well-defined function. So let's call this function g, or we'll also refer to it as f inverse. Okay, so if f is invertible, okay, we can define a new function g, or f inverse, his domain now is the range of f. Okay, and whose range is going to be the domain of f. And how do we define it? We say, well, g of y is equal to x if x came from y. Okay, and this will have the property that g of f of x is equal to x. So this inverse function undoes the original, right? So if I go from here, from x, then I take f of x and I get to here, then g of f of x will take me right back where I started. So this is the inverse function. Okay, so if I come back to my favorite example over here, one question that we could ask is this capital F, is this invertible? You know, given that we're restricting this to our range, is this guy an invertible function? Okay, Gabriel is shaking his head. Why not? Go for it.
Because we have the x squares and the y squares, there's that symmetry with x and y.
Right. So you know, anywhere in here, this certainly came from somewhere in R2. That's not a problem. But points in here in general could have come from more than one location in here. And we see that right here when we try to solve for x and y. Sure, I can find solutions, but I can find multiple solutions. Right? In general, I could find 4 different solutions, depending on whether I take the positive or the negative square root. So if I come back to this example, okay, I can cheat here. You can't do this in your notes very easily, sorry. If I come back to this example and ask, is this invertible? Then the answer is clearly no, because there's not a unique solution. So the solution xy of uv equals f of xy is not unique. Okay, so that's going to be one of my favorite examples today. Then the other favorite examples that we want to learn from is the linear setting, right? Because we know a lot about what happens in the linear setting, and we're going to get at least some intuition there about what we could expect and what things will definitely not work. Right? Not everything translates immediately from linear to nonlinear, but some might. And if we have some ideas of what things might, then we can, you know, move to examples like this and try them out a little bit more. Okay, so let's take this example first of all. F of xy equals 2x plus y and x minus y. And ask, is this invertible? Okay, well that asks me to find a solution of uv equals f of xy. This is linear, so I could write it in a matrix vector form. And I take a quick run through this 2x2 system, and I find that indeed I can find a solution, and my solution is going to be x, y are equal to u plus v over 3 and u minus 2v over 3. Okay, this is a unique solution, right? I found a solution. There's only one. Any uv I care to put in here will give me back a solution, no problem. So this is an invertible example. All right, one more linear example. Maybe I'll ask you guys to tell me if this one is invertible or not. F of xy is equal to x minus y and 2y minus 2x. Is this invertible? No. Why not?
Because the matrix is non-invertible.
The matrix is not invertible, right? So indeed, this is something that one could solve. There's a solution, but there's too many solutions. There's infinitely many solutions. Okay, so particular, let's see, if we want to make this equal to, say, well, if y is equal to x plus c, say, then what do we have? So if the right-hand side is consistent with this, we get lots of solutions, right? Otherwise, not so much, okay? So this is going to be non-invertible. And you've identified, I think, the key difference between these two examples. Here we have a matrix that's invertible. And you can tell that easily, right? You compute the determinant of this. The determinant is not 0, so we know this is an invertible matrix, so we know we can solve the linear system. This guy, if I look at the matrix, this matrix has determinant 0, right? So we know it's not an invertible matrix. We're either going to have no solutions or infinitely many solutions. Okay, so let's dig into these a little bit. Let me call this example 1 and this example 2. Okay, so in example 1, f of xy had the form a times xy. Okay, where A is an invertible matrix. Okay, and in this case, if we want to solve for this, so f inverse of, let's say, uv, this is something that we could, I mean, I wrote down the solution here. But this I can also write as in terms of a matrix, in terms of the inverse matrix. Right? So I could write this as A inverse UV, because this is a linear system. Okay, and this is what we expect in general for linear systems, that it's inverting the matrix that gives us the information. Now, the question is, how does this extend to nonlinear problems? Because in general, we're not teaching a linear algebra course here. We're trying to do some more sophisticated problems, which is not to say that linear algebra problems are not sophisticated. They're hard too, but they're not the kind of hard that we're talking about. All right, so what's the big deal about nonlinear functions? We want to work with nonlinear functions. We want to take on board what we know about linear functions. So let's just think about this for a moment and think about what kinds of nonlinear functions we might hope to work with if we want to be able to say they somehow behave like linear functions and we can learn a lot from linear functions. Okay, quadratic. Quadratic is an example of a simple function, but what else in general? When do we have functions where we say, at least in a small sets, they sort of behave linearly? Differentiable. Yeah, this is how we define differentiability. We said if we have a differentiable function, locally it looks linear, or pretty close to linear. Okay, and that's why we have some hope that we might be able to learn something from this case. Because if I zoom in on my nonlinear function, at least in a little neighborhood of the area I'm zooming in on, it should look a whole lot like a function of the form ax. So that's what we're going to try to go for here. Say, what happens if I treat my nonlinear function locally like a linear function? So this is our key idea. Differentiable functions look locally linear. Okay, near our reference point. Now, of course, there's a catch in that. if my nonlinear function isn't going to globally look like a linear function. It's just not. It's going to do whatever it wants to do far away. So any results we're going to come up with using this framework are going to only hold in a small set, in a neighborhood of x naught. OK, and that's clear without 1D example. OK, this is a nice differentiable function. So if I pick this as my point x naught, I can see great. Locally, this looks quite a bit like the tangent line. So maybe I can draw some conclusions in this neighborhood. All right, and in particular, if I restrict to just this neighborhood, I've got a beautiful invertible function right here. But clearly, this is not globally invertible. All right. So this is the catch. We can expect only local results. So at best, we can hope for local invertibility. So a function that is invertible if we restrict it to an appropriate subset of the domain. But if we're just using what we know about linearizations, we can't hope to extend that to the whole domain, because the function doesn't look like it's linearization on the whole domain. OK, so let's look at function restrictions. So we're going to consider functions of this type, like x squared, that may not be invertible, but they are invertible if we restrict them to a subset of the domain. OK, so in other words, if S is a subset of the domain, and if x and y are 2 points in S that are not equal to each other, then indeed we get different outputs. OK, so we're going to just find this restriction of the function. So we're going to take our function f and just shrink its domain, essentially. OK, so we'll define a new function on a smaller domain. OK, and so we're going to call this f sub s. And it's the same as our original function, but now it has a different domain. So now the domain is S. And now we're going to hope that this function is invertible, even if our original is not. So this is the restriction, and Fs inverse is the inverse of f restricted to this set. OK, so what would we do in an inversion problem here? We'd say, all right, we're trying to solve f of x equals u. We say, oh, shoot, there's 4 different places that this could have come from. But then we say, hey, hang on, take a deep breath. Only one of those points came from S, and that's the one that we want. Right? So in our earlier example that I erased, where we said, oh, we could take 2 different possibilities for the square roots for x and for y. It's a problem, but then if we say, oh, S is just the first quadrant, then we say, now we know we need to take positive square roots. Okay, and we're going to call a function locally invertible at a point if we can do this. All right, so I have a function, it's not invertible, but I zoom in on a particular point. I'm going to say, if I can find a little neighborhood of that point on which f is invertible, then I have a function that's locally invertible. And I move to a different point, I may need to consider a different neighborhood, but again, I can do this. So this we would call local invertibility. So if x naught is in Rn and there exists some neighborhood of x naught on which f is invertible, okay, then we're going to say f is locally invertible at this point. Okay, and if f is locally invertible everywhere on a set, then we're going to say it's locally invertible on the set. Okay, so let me come back to my quadratic example, which we already know what the solutions look like. Okay, and we said that x has got to be plus or minus the square root of u plus v over 2, and y is plus or minus the square root of u minus v over 2. And now I'm going to consider a smaller set, not all of R2. So let's restrict to this set. Okay, so clearly I could restrict to any quadrant, right? And I'm in business. But I can do more than that, actually. So I can restrict to almost all of R2. I just have to throw out the axes. F is not invertible on this set, clearly, right? Because, again, x could be positive or negative, y could be positive or negative. Okay, so f is not invertible on S, but okay, so I'm going to exclude this line, and I'm going to exclude this line. Now you give me any point you want in S. Maybe you give me this point. Is my function locally invertible at this point? Sure, right. This is clearly inside of one quadrant. I can draw a little ball around this that's going to stay clearly inside of this quadrant. Okay, so if I were to restrict my domain to just this little ball, I would be able to invert my function. No problem, because I know that when I go to invert my function, everything on here has positive x, negative y. Okay, so f is locally invertible at this point. Now you give me another point. Maybe you decide to give me this point over here. And I can ask the same question. Is f locally invertible at this point? It is, for the same reason. Once again, we're definitely inside one quadrant here. I can draw a little ball around here that is still clearly inside of one quadrant. And that means I could invert my function in this little ball. And I wouldn't get the same value of the inverse that I got over here. It would be different, all right? But I can still come up with a local inverse. And in fact, I can do this anywhere on my set S. The only problem would happen if I was lying on one of these axes, and then any neighborhood I draw would span multiple quadrants. But I've excluded that. I can come arbitrarily close. I can come very close. And that just means I need to draw a really tiny neighborhood. But I can do that. OK, so my function on this set where I've kept almost all of the points there are, my function is now locally invertible. Right? And again, the particular value of the local inverse is going to change depending on where my reference point is. But wherever I go in this set, I can build a local inverse. So F is going to be locally invertible. OK, so local invertibility feels like something I can maybe hope for, right? And even on a badly ill-posed system here, I didn't have to do much to make this locally invertible. OK, let's see what else we can learn maybe from some of our 1D problems or linear problems. OK, this guy, not invertible. Right? And what's kind of the key property of this function that makes it not invertible?
Symmetry.
OK, symmetry, but I wouldn't need symmetry to make something not invertible. It's not one-to-one, yeah. It's not monotonic.
Even?
It's even, but that, it doesn't matter that it's even. I could have a function like this that's also not one-to-one, not invertible. The problem is these points where the function turns around. Right? So the function was doing fine out here. It's just tracking along, minding its own business. Every value of x is giving me a new value of y until we get to here, and the function turns around. What happens at the point where the function turns around? It's got a zero derivative. Right? Of course, the zero derivative doesn't guarantee a function is going to turn around, but if the function is differentiable and turns around, we've certainly got a zero derivative. So here the problem arises because f prime of 0 equals 0. OK, we see something like that with linear systems too. So, if f of x is linear, okay, and the determinant of a is 0, we don't have invertibility. Now, if f is nonlinear and we do this linear approximation locally, what does the matrix come from? The linearization, yeah. What's the name of this matrix? The Jacobian matrix, right? OK, so for differentiable functions, right, locally we have f of x is approximately equal to, right, some constant term plus the Jacobian times x minus x naught. And it's this guy that's playing the role of a. Right? If we treat this as linear or an affine mapping, this is my A matrix, my constant matrix. So it would be natural to ask, maybe if we want to be able to go from local invertibility, this guy here is locally invertible except at the origin. It's locally invertible almost everywhere, and it breaks at precisely the point where f prime is equal to 0. So it would be natural to ask, I think, if we're going up to higher dimensions, suppose I have a differentiable function and its Jacobian never has a 0 determinant. Maybe I can boost myself from local invertibility to global invertibility. Somehow I'm not turning around in this way. So this is a natural question that I would want to ask if we're exploring these things with simple examples. Because somehow, given the 1D example, given my linear examples, this seems like to be the theme, that if this guy is 0, we lose local invertibility at those points. If it's non-zero, we're kind of in business and can invert everything. So this is a question I would probably ask. If the determinant of is not equal to 0 for all x, is f invertible? You have intuition here? Yes? No? Any wild guesses? You think yes? It seems natural to say yes here because it works for the linear case. It works in one dimension for the nonlinear case. Unfortunately, the answer is actually no. So 1D is just absurdly simple sometimes, and it just doesn't capture everything that can happen in Rn. Linearization issue is also absurdly simple because it just only works locally and simply won't tell us what's happening globally. So here's an example. I would have guessed yes, too. This is how we build up theorems, is we try some simple cases, see a pattern, and then say, I wonder if that's a theorem, and then try to prove it, and either we succeed or, after a few months, we give up and say, maybe I should look for a counterexample. All right, so let's try this example. E to the x cosine y and e to the x sine y. The Jacobian is, all right, partial of this with respect to x and with respect to y. And then the second line. All right, the determinant of the Jacobian equals, this times this is e to the 2x cosine squared y minus, this times this becomes a plus e to the 2x sine squared y, which is just e to the 2x. The exponential function is never 0. Okay, so this is not 0 for all x and y. All right, so this Jacobian is always invertible, no matter what value of x and y you throw at it. Okay, so we've satisfied the hypothesis here. Now, if we go back to this function, is this function invertible? Why not? It's the periodicity, right? This function has no idea if I've plugged in y equals 0, or y equals 2 pi, or y equals 4 pi, or y equals 6 pi, right? Every time we jump y up by another 2 pi, we get the same answer again. And we get the same answer again. So in general, we're going to expect to have infinitely many solutions when we try to invert this. So this is not invertible, yeah.
That also has something to do with the fact that we can put infinite y into the determinant equation and we can still get a non-zero answer. Because the determinant, as you see, only depends on x.
The determinant only depends on x, so yeah, that may be a factor. I mean, you could get cancellation happening where that probably wouldn't be a big deal. But you know, there may be something there too. Or you could have cases where y still comes up here and it's non-zero, but problems still happen. But the periodicity certainly kills you here. All right, so here we're going to have invertibility on a strip. Okay, so a strip of this form S is points in R2. And an x is not a big deal. You can go through here and solve for x pretty easily. The problem is that, of course, with the periodicity, you can only let y change by less than 2 pi before you start getting repetitions in the function value. Okay, for any real number a. Right, so I take R2, right, I pick some reference point where I want to start. So here's a plus 2 pi. As long as I stay inside this strip, I can invert. I can solve for x, I can solve for y uniquely, but as soon as I want to jump outside of this strip, I've got non-uniqueness now in my y because of this periodicity. Okay, so f is invertible, restricted to domains of this type. F is locally invertible everywhere because you give me any x and y you want. I'll build a little strip around it and no problem, or build a little ball around it, whatever, and I can invert. But I don't have global invertibility despite the fact that my Jacobian is perfectly well behaved here. So that suggests something to us. If we're trying to build up some kind of inverse function theorem, we're probably not going to be proving global invertibility. It's just, you know, all the obvious things that we would want to check, they just don't give it to us. Probably the best we're going to hope for is local invertibility. Yeah?
So this happens because the sign of the, this is the question. So the monotonicity in multiple dimensions, we don't check it just with the determinant, right?
Right, we're just checking the determinant, which is one number, certainly.
We only check these.
We only checked the determinant, yeah. So you're saying, is the issue because there's this non-monotonicity in the other directions?
Yeah.
Right, that can be related. It's not as simple as that in higher dimensions because there's this mix between x and y. So it's not always as clear as saying, you know, the function is going up or the function is going down. But yeah, I think that's playing a role in here too. But again, it's something that's difficult to get a handle on and say, here's a really simple test that will tell you whether this is going to be global invertible or not. Whereas in 1D, there's a simple test. Is the determinant ever 0? Is the derivative ever 0? For linear problems, there's a simple test. Is the matrix invertible? And you know that your function is always going to just keep traveling with the same matrix.
But if you prove that it's, let's say, increasing?
If in a special case where if you proved it was increasing or decreasing in both variables, sure. You could come up with simple settings like that. Most of the problems that you're going to want to look at out in the real world are probably not going to be as simple as that. So what is our goal, I guess? Is to come up with criterion we can check, but also criterion that we want to use later. So we could prove, we can build simple criterion maybe that give us what we want, but then we go out into the world and say, the world doesn't fit these criterion. So this, I think, is one conclusion. When we build an inverse function theorem, the best we hope for is local invertibility. So the best we can hope to prove in general is something about local invertibility. And when I write down a candidate for the high inverse function theorem, I'm not going to have my conclusion be f is invertible, because I'm starting to think that's going to be too hard to prove under a realistic set of assumptions. The other thing we can talk about a little bit is what is the Jacobian going to look like here. Okay, so if f of x is linear, okay, and of course the Jacobian is equal to the matrix A. Then we said it was easy to write down the inverse in this case. F inverse just came from doing the inverse matrix multiplication. Okay, and we could also write down the Jacobian of this guy, which was A inverse, which happens to be precisely the inverse of our original Jacobian. So this is another question we can ask. Is this something that is likely to happen in the nonlinear setting, that I can relate the Jacobian and the inverse Jacobian in this way? That would be nice. That would make it very easy to compute the inverse Jacobian. And this, it will turn out, does push through. And we'll be able to prove this pretty easily. So we'd love to be able to say something about this. To push this through to the nonlinear case. Okay, so let's give ourselves some language for this. The kinds of things that we're trying to look for are going to be what we call regular transformations. Okay, so f going from Rn to Rn is regular. On an open set S, if f is as nice as we could like it to be on this set. So if f is invertible, okay, so we'll be given a function, right, that's defined maybe on all of Rn or on some big domain. We'll be hoping to find local sets on which it is invertible, even if it's not globally invertible. We're going to want it to be continuously differentiable. You know, we should have some sense that differentiability is important, because that's what lets us relate locally, at least, to something that's linear. Without differentiability, we cannot do that. So let's try to build this in as our requirement. And we should also probably want to keep ourselves in this setting where the Jacobian is invertible. Okay? We know that doesn't give us global invertibility in general, but it's probably important. You know, it's necessary for the linear case. So if our theorem doesn't work in the linear case, then that's not so good. Okay, so we're going to also ask that the determinant of the Jacobian of f is non-zero on S. Okay, so something like this, right, would be regular as long as we restrict to sets S like this, right? Because, what is this? This is invertible on that set. The Jacobian is beautiful and continuous and invertible, no problem. So this is the kind of function that we expect we might be working with. Not that it's globally invertible, but we can find a set on which it's perfectly well behaved and does all that we want. So let me write down a conjecture. Let's try to build in all of the pieces that we've kind of thought about today. What we think might work, what we're pretty confident won't work, we won't put into the theorem. Okay, so let's start with a function. F that is continuously differentiable. Okay, on an open set S. Why an open set? An open set means it's guaranteed to take up space, take up actual volume in Rn, right? So I don't want to say that I'm working in R3 and then have S be just like a straight line and somehow this function is only well behaved on a line embedded in R3. I want my function to like be well behaved in an actual volume. So that's something that working with open sets guarantees us, because an open set means I can build a ball around points in there that takes up space and that stays in the set. Okay, so we're on an open set, and my Jacobian is invertible on S. Okay, now what am I hoping for? I'm hoping for local invertibility on this set. Okay, so I've started with a function that's well behaved on some nice domain. I still don't expect global invertibility on this domain. I expect local invertibility. So what does that mean? That means I'm going to pick any point in the set. And what am I hoping? I'm hoping that I can build a little neighborhood around this, some open ball, some open set on which my function is invertible. Okay, so I pick any epsilon I like in the set, and I'm going to hope that there exists some open set, which I'll call N, of x naught, on which f is regular or invertible. Okay, so this is what I'm hoping. I can build an open neighborhood where f is invertible. I'm hoping for maybe a little bit more than that. I'm hoping that my inverse function is also a really nice, well-behaved object. So in particular, maybe I'm hoping that my inverse function is also defined on a set that takes up volume. So I don't want f to take my set n and collapse it onto a line or a point or something. I want it to take my set n that has volume and map it to something that has volume. And now I have a new domain for my inverse function that has volume and hopefully kind of behaves nicely in a symmetric way. So I'm going to ask that, moreover, f of n is open. Okay, this is going to become the domain for my inverse function. So all that I'm asking for now is that, again, I have a nice domain for my inverse function, has volume, takes up space. Okay, and I want to be able to say that my inverse function is also nicely behaved. So G is going to be the inverse of f restricted to this set. Okay, this has all the nice properties too. It is continuously differentiable. Okay, on its domain. Okay, and I'm hoping to be able to see this kind of relationship between the Jacobians. Okay, and the Jacobian of G is equal to the inverse Jacobian of F if y equals f of x. So this, I mean, this is a technical statement, but it kind of brings together a lot of the intuition that we've tried to build up here. I hope this builds up some of the intuition we've tried to build up here. Are there any questions on this statement? I mean, it's long and it's technical. The statement seems technical, but I hope we have a bit of intuition into what we're trying to do here. So this, I've labeled this conjecture right now, because this just, again, is our hodgepodge of intuitions. But this conjecture has a name. This is the inverse function theorem. So what I'm going to do now, I think, is just do an example of using this. And then next class, I will ask you to buckle your seatbelts, and we're going to try to actually prove this rigorously, okay? But I cannot prove this rigorously in 10 minutes. And we're going to take with us all the intuition that we built up today. Well, first of all, to write this down. And then we're going to try to use all that intuition, pictures that we've drawn, to help us come up with a good proof of this. So let's just take an example here. F of x, y, z is equal to x plus y plus z minus 1 squared plus 1, y plus z plus x minus 1 squared minus 1, z plus x plus y minus 2 squared plus 3, and x naught is equal to 1, 2, 1. Okay, so under the assumption that this is a theorem, it's not a theorem yet, it's a conjecture, but if this is true, let's see, are we in a setting where we can use it? Well, f is certainly continuously differentiable, and that's no problem. It's continuously differentiable on whatever domain you like. I guess we better check its Jacobian. So the Jacobian of f is equal to 1, 1, 2 z minus 1, 2 x minus 1, 1, 1, 1, 2 y minus 2, 1. Let's just plug in our point x naught. Okay, so at x naught, we're going to have 1, 1, 0. This is going to be 0, 1, 1, and then 1, 0, 1. Okay, we could compute the determinant. Okay, and let's see, what do we get? We get 1 times 1 minus 1 times 0 minus 1. And then that's a 0. So this is not 0. So that's good. So if the Jacobian determinant is not 0 at this particular point x naught, that means it's also going to be not 0 in a neighborhood of x naught, right? Because we have continuous differentiability. This Jacobian is a continuous object, and it can't jump from 2 instantly to 0. So this holds in some neighborhood of x naught, okay, by continuity. And that means this inverse function theorem applies. We've satisfied all the hypotheses. And in particular, that means, at least locally, we can build up an inverse of this thing, which is maybe not totally obvious, right? Now we've got a nonlinear object. We know that, we could certainly build quadratic functions in 1D that, you can't solve. So it's by no means obvious that you'd be able to build any kind of inverse on this, but now we know we can. Okay, so this guy, which is the inverse of f on some neighborhood, is defined on some neighborhood of my reference point. How do I compute u naught? F of x naught, okay? So my new reference point in the u space becomes f of x naught. Okay, so I plug 1, 2, 1 into there, and I should get 4, 2, 5. And now I know that I can invert this function in a neighborhood of this point, which again, I wouldn't know that just staring at that. It's not obvious. And in general, for this case quadratic, maybe you can work things out here. In general, with non-quadratic things, it may be highly non-obvious whether you can do this. But actually, there's some very simple things to check that give us this information, that we have local invertibility. It doesn't mean the inverse function is easy to write down. Even in this case, it might not be easy to write down. Non-quadratic, you're probably not getting off the ground. But we can approximate it quite well. Because what do we know? Assuming this theorem is true, we know that G is differentiable. That means it's locally well approximated by its linearization. For linearization, what do we need? We need a reference point. Okay, we have a reference point. G evaluated at this point is going to take us back to x naught. And we need a Jacobian. Well, in general, we're not going to compute G exactly. We're not going to compute its Jacobian exactly, but I can do it at my one reference point, right? Because at this reference point, all I have to do is take this matrix, which I've already computed, and invert it. And that will be precisely the Jacobian of my G at my reference point. So I have everything I need to write down a linearization of G about this point. And that means I have everything I need to at least estimate my inverse function, my local inverse function. Okay, so we know that G of u naught is x naught, which was 1, 2, 1. We know that the Jacobian of G at u naught is the inverse Jacobian of f at x naught. Okay, and this you can compute. It becomes 1 minus 1, 1, 1, 1 minus 1, minus 1, 1, 1. And all of a sudden, we're kind of in business here, at least near the point u naught. We're going to have that g of u is pretty close to, all right, g of u naught, which is 1, 2, 1, plus its Jacobian. Okay, times u minus u naught, where u naught was 425 here. Okay, and this works because our inverse function is also beautifully well behaved and differentiable and defined on this open space set that has volume. So since G is differentiable. Okay, so the inverse function theorem is going to do a lot for us. And of course, this f was quadratic. But you can imagine that I could have taken an f with a very complicated form, right? And this wouldn't have been any harder to do, right? The hardest thing to do maybe is to compute the Jacobian and invert it. But computing derivatives is easy, right? Oh. Taking an inverse of a small matrix is easy. Big matrix is a different story. All right, so even for very complicated functions, we can say, here's a good local approximation of the inverse. So this is going to do a lot for us. And again, next time we're going to try to turn that conjecture into an actual theorem and go through the proof rigorously and convince ourselves that it's really true. So I'll leave you there today, and we'll pick this back up next class.